At the end of today's class, we left off by having completed this particular slide. So we had filled out this chart that related the value of ln b, that is the natural logarithm of the base for these exponential functions that are listed here. And we were able to equate those or see the similarity in those values when compared to the slope at x function, where we were taking the difference quotient, we were substituting in the value for h, and then determining the slopes of the secants at x equals 0. And these here represent the slopes of the secants. Okay, which we had then seen were equal to the natural log of b. Okay, you can see the similarity between these two columns here. And those are the answers we had provided in both parts D and part E. So what we're going to do now is it's all fine and good to say that we have this expression in our table, but let's see if we can't use another tool here in calculus to come up with an expression that represents the natural logarithm of b. Okay, so let's take our first principles definition. So that is dy by dx is the limit as h approaches 0 of the difference quotient f at x plus h minus f at x all over h. So being that we are dealing with the function y equals b at x, let us rewrite this statement as the limit as h approaches 0 of b to the x plus h minus b to the x all over h. So it just so happens that if we are interested in the value of the slope function at x equals 0, or the derivative at x equals 0, then we're going to go ahead and substitute in a value of 0 for x. So let's see what we have here. So the limit as h approaches 0. So that would be equal to b to the h minus b to the 0 all over h. Now if we move a little further on that, up here to the top right hand side, so that will be equivalent to the limit as h approaches 0 of b to the h minus 1 all over h. So what we're saying in this for now is that we have an expression for the y-intercept for the derivative function, right? At x equals 0, here's what we have. Okay, so at x equals 0, this represents the y-intercept of the function. Okay, so I'm just going to label a few things here. Y-intercept. We also saw that it was, in this case, in all cases, it was that stretch or compression factor applied to y equals b to the x to get or to arrive at the derivative function dy by dx. We can also then appreciate that based on the table, the values that were calculated here, that we have an expression for the logarithm of b, okay, using that difference quotient. So we have also the ln of b, okay, which is the limit as h approaches 0 of that particular rational expression, b to the h minus 1 all over h. So far, we have a definition that is a rule that is going to work for finding the derivative of that function specifically at x equals 0. And that's what that does. Well, it's all fine and good, but still not that user-friendly. It would be better for us to have a derivative for the function y equals b to the x for all x. Not just for x equals 0, but what do we do in cases where we have a function and we need to find its derivative? It's not enough to say that we have an expression for x equals 0. We need more than that. So let's go back and repeat the process, but we'll approach this a little differently. Okay, let's go very general. Okay, let's just say that we'll find the derivative of the function as h approaches 0. We're not going to find it at 0, but in general, let's try this. What we're going to have, okay, is we're going to do a little factoring in the numerator, much like we had done earlier in this unit. So let's re-express here b to the x plus h as b to the x multiplied by b to the h. And we'll subtract b to the x from that. Well, as you can see here, let's just change colors here and differentiate between lines of our solution. If we common factor out b to the x, okay, take b to the x out, and you're going to be left over with b to the h minus 1 all over h, okay, in the numerator. Moving forward, what we're going to do is we can apply particular properties of limits. Okay, so using the limit properties that were established, that were used at the beginning of the course, what we're going to do is divide the limit into the product of two limits. Okay, now recall that when you're multiplying fractions together, you're allowed to split the numerator. Okay, so numerators get multiplied together, as do the denominators. So I'm going to take the limit of b to the x as h approaches 0, and I'm going to multiply that by the limit as h approaches 0 of what we have left, which is b to the h minus 1 all over h. Now, because b to the x remains constant, okay, so since b to the x remains constant, as h approaches 0, we know that we can take that and simply write it as b to the x. So no matter what h is, b to the x is going to be b to the x. That remains constant. And multiply that by the limit as h approaches 0 of b to the h minus 1 all over h. Well, there's something really neat, really cool going on here, is if you focus on this piece here, okay, you're going to notice, let's take a trip back here for a second, we have the same thing happening here, okay, where we said y-intercept, ln b, stretch factor, okay, so we take that particular value and we multiply it by b to the x, okay, and that will give us the derivative of exponential functions in the form y equals b to the x. So b to the x times the natural log of b. Okay, so just in the space below, let's summarize. So, therefore, the derivative of the function b to the x with respect to x is none other than b to the x ln b. Okay, so we're going to use this to our advantage tomorrow in differentiating exponential functions. And just a few key points before we go. These are from your textbook, page 256, 74, and 264. It's just a summary of what we've seen regarding E, or Euler's number, and the derivative to y equals b to the x. So please read them through. If you have any questions regarding this information, then please bring them forward to class tomorrow.